Welcome to this explainer. Today, we're going to explore something truly mind-bending. For decades, mathematicians have wrestled with the Poincaré conjecture by physically trying to smooth and mold shapes in their minds. It's like trying to solve a giant, invisible puzzle. But what if we just threw all of that out? Today, I am so excited to introduce you to a completely groundbreaking concept, solving complex geometric topology using purely arithmetic and spectral geometry. Yep, we are talking about the Adelic Langlands Program. So consider this. What if we proved the Poincaré conjecture without ever touching a physical shape? Imagine trading all that physical cutting, pasting, and smoothing of geometric manifolds for a sleek, digital, mathematical data pipeline. We're literally talking about transforming topological knots into streams of pure numbers. Crazy, right? Well, let's dive into this and see exactly how this mathematical alchemy actually works.
All right, here's the roadmap for our masterclass today. This is going to help us unpack some pretty dense formulas step by step. We'll start with beyond geometric surgery, then cross the Langlands bridge, followed by matching the L-functions. After that, we'll look at filtering exotic spheres, the Adelic gluing law, and we'll wrap it all up with information conservation.
Okay, part 1, beyond geometric surgery, going from cutting to filtering. Now, you might already know how fractured traditional proofs used to be. For high dimensions, mathematicians used geometric surgery to safely cut and paste manifolds. Down in dimension 4, they had to use these incredibly complex, non-smoothable disks just to deal with singular crowding. And for dimension 3, well, Perelman famously used Ricci flow as surgery. But here's the game changer. The Adelic method unifies the whole shebang. There is zero physical surgery required for any dimension. Instead, each dimension is just cleanly mapped to a specific mathematical axis or scale.
And this slide brilliantly illustrates why this unification is possible. Changing the dimension of a manifold in the Adelic framework doesn't break the math. The underlying arithmetic numbers, the p-adic numbers, they completely eliminate that geometric crowding. So changing dimensions simply shifts the weight, or S, of the corresponding L function. Dimension 3 maps straight to the critical axis, where S equals 1/2, and dimension 4 maps to the physical mass scale, where S equals 1. Those classical geometric blockages literally just dissolve.
Moving right along to part 2, the Langlands Bridge, taking us from arithmetic to automorphic.
Notice the absolute perfect mathematical duality we've got going on here. On the left side, we have our arithmetic side. This represents localized geometric topology, the physical knots, the twists, the monodromy code in a topological space. But then, the Langlands correspondence acts as a bridge. It takes that tangled knot and transforms it into the right side, automorphic representations. These are incredibly smooth, oscillating harmonic wave fields distributed globally across an Adelic space. We're translating a physical knot into a smooth wave.
So let's look at the exact mechanics of that translation. This equation right here is the Satake parameter. Basically, at a finite, unramified prime, we extract local arithmetic data called Frobenius eigenvalues. That's those alphas you see on the diagonal matrix. This perfectly captures the non-abelian monodromy. Then, the trace operator translation right below it maps this exact matrix to the local Hecke eigenvalues on the automorphic side. By taking the sum of those eigenvalues, the trace operator flawlessly translates that arithmetic code into a continuous spectral wave function.
Which brings us to section 3, matching the L-functions, or the global identity.
Now, to glue these local patches together across all scales, we require absolute mathematical symmetry. Follow this equation with me, left to right. On the left, we have the arithmetic Artin L function, which is the S weighting of our fundamental group. On the right, the automorphic principal L function, which is the S weighting of the spectral wave. For this whole theory to hold water, these two have to be perfectly identical. The arithmetic invariance must mirror the spectral invariance flawlessly, no exceptions.
So how do we mathematically enforce that mirror image? That's what this is, the explicit global Langlands map formula. I know, it looks dense, but let's deconstruct it piece by piece. On the left is our output state, the unique automorphic wave function. It's generated by a global integration over the quotient space. Right in the middle, we have our gluing data, a tensor product of traces that glues those local Satake parameters across all primes. And then, at the very end, we have the ultimate smoothing agent, the Fourier-Mukai kernel. That is the engine smoothing our abstract data back into macroscopic space.
Okay, now that we've seen the heavy equations, let's just cleanly map out the step-by-step pipeline to prime your brain for what's next. First, we inject the spectral data via the Dirac operator. Second, we filter it through Legendre projection and J-theory. Third, we apply Langlands L-function rigidity. And fourth, we match it to the standard sphere.
This exact sequence leads us to a pretty inevitable conclusion.
Let's walk through how this works. We start with the homotopy sphere, a manifold with 0 internal data holes. Because it has no holes, its global completed L function perfectly reflects without any non-trivial poles or zeros. And this is where the Langlands rigidity theorem steps in. An unramified representation with a trivial root number is completely 100% unique. So when this unique representation is pushed forward through the Grothendieck-Riemann-Roche framework, it undergoes a rigid collapse. It literally has no choice but to form the constant positive curvature metric of a standard, perfect sphere.
Section 4. Filtering exotic spheres and detecting impurities.
So what happens when the math encounters an anomaly, like a wild, non-standard exotic Milnor sphere? To anchor this abstraction, we use a tool called the Eales-Kuper mu invariant. It essentially acts as an arithmetic trigger. Topologically, a Milnor sphere looks like a normal sphere, but its smooth boundaries are totally twisted. This invariant captures that hidden twist as a fraction, k over 28 modulo 1. If k is 0, you're good. It's a standard sphere. But if k is literally anything else, it flags a hidden exotic structure, an arithmetic impurity in the data stream.
And check out how this fraction translates into a real arithmetic breakdown. That denominator, 28, isn't just a random number. It's 2 squared times 7. This explicitly hardwires two specific prime numbers, 2 and 7, into the manifold's algebraic structure. When an exotic structure pops up, it forces a hidden local ramification event at precisely these primes. It violently breaks the unramified baseline of the standard sphere. Hidden smooth complexity just cannot hide from arithmetic geometry.
And listen, this local breakdown isn't just a math error on paper. The non-trivial inertia group actually truncates the data stream, which you can see right there in the local factor formula. This pumps up the global arithmetic conductor labeled n. When n is greater than 1, it shifts the entire baseline. When we push this forward to macroscopic 4D space, it generates a physical, non-zero localized topological stress energy tensor. Basically, the exotic sphere requires continuous external energy just to exist. Without it, it's inherently unstable and will decay right back into a standard sphere.
Almost there. Section 5. The Adelic gluing law, focusing on boundary conservation.
Gluing manifolds isn't just geometric plumbing, you guys. It's a massive information theoretic filter. Say we have manifold 1 on the left and manifold 2 on the right, connected by a bulk interior. To glue them together, they have to satisfy boundary conditions arithmetically. The Adelic eta invariant, that's the formula shown inside the bulk, measures the exact spectral mismatch across all primes. It guarantees that the transition between the two distinct spaces is perfectly accounted for in the spectral data stream.
Let's actually hold on to this equation for a second, because it is just beautiful to unpack. This is the functional factorization identity. The output wave state on the left equals the input wave state on the right, but it's heavily modified by the bulk spacetime in between. The bulk acts as a filter through the arithmetic conductor rescaling, and it applies friction via a continuous phase shift. This brilliantly illustrates something profound. The arithmetic conductor rescaling elegantly proves T-duality in string theory. If the geometric boundary shrinks, the arithmetic primes cross-shift to compensate. The total Adelic information budget across all fields is flawlessly, completely conserved.
Finally, Section 6, Information Conservation, the ultimate reduction.
So, to summarize, here are your core physical takeaways. Number 1, topology is ultimately about information conservation. If a closed manifold has trivial homotopy, its data stream fundamentally lacks the complexity to build alternative stable shapes. Number 2, exotic structures, like those Milnor spheres we talked about, are really just temporary quantum fluctuations that radiate away. And number 3, the standard round sphere is the only globally stable configuration in macroscopic spacetime.
And as you can see here, the Fourier-Mukai kernel and the Grothendieck-Riemann-Roche push-forward absolutely guarantee this inevitable outcome. Any quantum topological distortions, any local ramifications, they'll all eventually melt away under the geometric relaxation of J-theory. They shed their anomalous energy until they slide all the way back down to the absolute minimum energy state. The standard, smoothly perfect sphere isn't just likely, it's inevitable.
Which leaves us with a pretty provocative question to wrap up this explainer. If the very fabric of macroscopic spacetime, its shapes, its stability, its boundaries, if all of that is strictly governed by these rigid mathematical L-functions, is the physical universe ultimately built on pure arithmetic information? Like, is reality itself just a reflection of conserved, perfectly balanced Adelic data streams? It is a wild, fascinating concept to ponder. Thank you so much for joining me on this deep dive today.